The first part of this lecture is about evaluation context. So let's review the formulation of simply typed lambda calculus. Simply typed lambda calculus. So we have these syntactic categories. Type is either this base type or this function type. And for base type, we can include as many base types as we want, but for simplicity, let's just use this Boolean base type. And for expressions, we have variables, lambda abstractions, and application. And for this Boolean base type, we have this if conditional expression and true and false. And the set of values include this lambda abstraction and Boolean constant true and false. So this is the syntax for the simply typed lambda calculus. And for reduction rules, let's assume call by value. In the case of call by value, we have these reduction rules. Expression E1, E2 reduced to E1 prime, E2, if E1 reduced to E1 prime. And if everything goes okay, we will have something like lambda x a dot e applied to value expression E2. In this case, we try to reduce expression E2. Then we have applied to E2 prime. And again, if everything goes okay, then we will have lambda abstraction applied to value v, in which case we perform beta reduction. If we have this if-then-else expression, we first try to reduce this expression, conditional expression. If this guy reduces to expression e prime, the whole expression reduces to if e prime, then e1 else e2. And if the whole expression is well typed, so the reduction goes okay, then eventually we will have perhaps if true, then e1 else e2, in which case we simply take the first then branch. And there's the symmetric case where the conditional expression is false. So these are the reduction rules under call by value reduction strategy. And these are the syntactic categories constituting the abstract syntax of this simply typed lambda calculus. And what we want to do today is to develop an alternative formulation of this operation semantics, which is based on this set of reduction rules, but we will try to find a more elegant formulation of the operation semantics, a more elegant but still equivalent operation semantics. So here is the basic observation. So under these reduction rules, suppose that we have a reduction, say expression E reduced to E prime. And these are reduction rules. So if this reduction is valid, in other words, if expression E indeed reduces to expression E prime, then we should be able to build a derivation tree. It's just a judgment. So this is valid judgment. And if there is a proof for this valid judgment, then we should have this derivation tree. Derivation tree where we compose these we compose applications of these reduction rules. And because this is derivation tree, at the end of this derivation tree, at this position of leaf, here, we can have either this rule or this rule or the other rule for if of then E1 else E2, this reduced to E2. So at the end of this derivation tree here, so this is the root of the derivation tree, this is the root, and at the end of the other spectrum, at the other end of this derivation tree, so at this position of a leaf, we have either this rule, an application of this rule, or this rule, or this rule. Not these three reduction rules, because these three reduction rules are not axioms. They have this premise. It has this premise, it has this premise, it has this premise. So the derivation tree cannot terminate with an application of one of these rules. It must terminate with, at this position, it must terminate with an application of one of these inference rules, which are all axioms. So here, for example, we can have lambda x a dot e double prime applied to value v reduced to v for x e double prime, something like this. So that's the the basic observation. So let's further develop this example. So from this example, if this expression e reduced to another expression e prime, then we should be able to find a sub-expression of expression e, something like this, which can be reduced to another expression by beta reduction. So in other words, if this expression e is reducible, so it reduces to another expression e prime, then somewhere inside the expression e, you should be able to find a red x. And this red x will appear at the position of a leaf in this derivation tree. So in practice, if you'd like to reduce this expression e, then you want to quickly find the red x inside this expression e. Then what you can do is just reduce this red x. So this red x becomes some different expression, and then you leave the rest as intact. So let's take a look at a concrete example. So this is the basic observation. Let's consider an expression e, which is some huge expression applied to expression e prime, and this huge expression is if then else expression if then e1 else e2, and the conditional expression itself is an application applied to value v. So let's consider this expression. So it turns out that this expression is indeed reducible. So it reduces to another expression. Then, as we have seen in the previous observation here, if an expression is reducible at all, then we should be able to find an expression, a red x, that can be reduced by one of these inference rules, one of these reduction rules. So in this case, inside the expression e, we should be able to find such a red x. And in this particular example, the red x is this expression. Uh, uh, so this expression is the red x, So if somehow we quickly find this red x, then we can reduce the whole expression just by focusing on this red x. If this red x is reduced, another expression, let's just say e double prime, then the whole expression reduced to then e1 else e2 e prime. But the crux of the problem is how quickly we find the sub-expression expression e, which must be a red x. So this example suggests that if this expression is reducible, we can visualize this expression e as the composition of two components. The first is red x, which is in this particular example, the red x is this one, and the rest of it is the rest. So this is the red x, so it's a valid expression. We are going to apply beta reduction to this red x, and the rest of it. And of course, the rest of it is not a valid expression. It is an expression with a big hole in it. So in other words, we can decompose the whole expression into two parts. The first part is red x. So we have this red x. And the second part is the original expression where we have a big hole in it. So this hole has been removed. So we can think of this expression E as consisting of this red x and the rest of it. And the rest of it, this one, is not actually an expression because it's a syntactically ill-formed expression because we have some funny hole inside it. And the second component, this is called evaluation context. It's literally context or a surrounding environment in which evaluation takes place. So if we think about the reduction of the whole expression, what happens is we are going to make a copy of the whole expression, the second component. So we made a copy of the second component. So we have a hole in it. And we are not going to touch this second component. We just have a hole in it. We are going to reduce the red x, and then put the result of the beta reduction here. So the result is phi for x in expression E. So in the course of reducing the whole expression E, so the whole expression E, this one now reduced to this one, we only modified the red x. We did not touch anything in the rest of the expression. And we decide to call the rest as evaluation context. So in other words, the evaluation context marked here stays the same. We only touch the red x, and the red x is going to be reduced to this new expression. So the red x reduced to another expression. In the meanwhile, the rest of it, which is called evaluation context, stays the same. In this regard, it makes perfect sense to call the second component, this one, something with a big hole in it. It makes perfect sense to call the second component as evaluation context. It's literally a context in which the evaluation takes place. And the evaluation is basically reducing the red x. So that's the key idea behind the evaluation context. So the idea is, again, given an expression which is known to be reducible, we know that this expression is reducible. Then we can decompose this expression into two parts. The unique radix. This radix is going to be reduced at the next step, and the rest of it. And the rest of it is basically the original expression with a big hole in it. And we are going to put this radix into this hole, and we recover the original expression. So that's the idea. And again, the second component is called evaluation context for good reason. It's literally context in which the evaluation takes place. So that's the idea behind evaluation context. And the position of this hole indicates where the next reduction actually takes place. Let's go back to this example. Let's decompose this expression into two parts. So we know that this expression is reducible. Then there must be a unique radix. I'd like to emphasize the word unique because this expression is reducible, then there must be a unique sub-expression that is going to be replaced by an application of a beta reduction. So we assume that the reduction strategy is deterministic. So this expression is reducible, so there got to be a unique radix somewhere inside this expression. And in this particular example, this is the unique radix. So now let me decompose this one into two parts. The first part is radix, lambda x a dot e, applied to value v. And the second is the rest of it. And the rest of it is basically the whole expression with a hole in it. And the hole is this one. And then E1 else E2 applied to E prime. So this is the second component. This is the first component to radix. So this expression E can be decomposed into the first component, radix, and the second component, evaluation context. And we can notice that the evaluation context literally points to the position where the evaluation is going to take place, which is this one. So this hole indicates the position where the reduction is going to take place. So everything makes sense now. So in summary, we'd like to remember the fact that an expression E can be decomposed into two parts. First, unique radix, and second, the rest of it. And the rest of it is called evaluation context. It's an expression with a hole in it, and this hole indicates the position of the next reduction. Now, let's further develop this idea of evaluation context. Suppose that we have a reduction strategy. We assume a unique reduction strategy, and of course it's going to be deterministic, which means that given expression E, we can't have two distinct expressions E1 and E2 that E can reduce to two. We can't have something like this. We must have only one unique expression if this expression is reducible. So the reduction strategy is deterministic, and because this reduction strategy is deterministic and it has been given, if we have an expression that is known to be reducible, then this one can be decomposed into first component radix, and the second component evaluation context. And evaluation context is basically an expression with a hole in it. So this is evaluation context. Because the reduction strategy is deterministic, its radix is going to be unique. That in turn implies that this evaluation context is also unique. So let me repeat again. under this particular reduction strategy, the way that this expression E reduces is unique. That means that this red X must be unique. And this in turn implies that the corresponding evaluation context is also unique. And we can further develop this idea. And what we obtain is unique definition of evaluation context. So in other words, if you are given a particular reduction strategy, of course it should be deterministic, then you can derive a unique corresponding unique definition of evaluation context. Because this reduction strategy tells you how to obtain an evaluation context from a given expression. So in some sense, this reduction strategy tells you how to locate a red X in a given expression. But that's precisely what these evaluation contexts are for. An evaluation context tells you where to locate the next red X. So in some sense, this reduction strategy and this definition of evaluation context, these two guides should be equivalent in some sense. And this observation leads to the idea that perhaps the reduction strategy will specify a unique definition of evaluation context. So that's the idea. So here is an example. So remember that reduction strategy tells you how to reduce a given expression. And reducing an expression basically amounts to finding the red X and then applying beta reduction. On the other hand, this evaluation context tells you how to locate the red X immediately, because you can just go to the position of this hole and then you can find the position of the next red X. So intuitively, this reduction strategy and the definition of evaluation context should be equivalent. That's what our intuition tells about the equivalence between these two. So here's an example. Let's assume call by value reduction strategy. And the question is, what is the corresponding definition of evaluation context? So evaluation context. And for historical reason, let's write the evaluation context using meta variable kappa. So this is the evaluation context corresponding to call by value. First, evaluation context is something with a hole in it. So of course we should have this hole. And we have kappa E, which corresponds to the situation where given an expression E1, E2, given expression E prime E, we are currently looking at this expression E prime. We are trying to locate the red X somewhere inside the expression E prime. And this component in the definition corresponds to this situation. And the next component is lambda x a dot e applied to kappa. And this one corresponds to this situation. We have some expression lambda x a dot e applied to e prime. And currently we are trying to locate red X somewhere inside the expression e prime. And finally, we have if kappa then E1, else E2. And if you have an evaluation context of this form, what that means is that you have currently some expression like this one, and you are trying to locate the red X somewhere in expression E. So that's the idea. So let me summarize again. This call by value reduction strategy tells you a unique way of reducing an expression. Unique way of reducing an expression. But reducing an expression has two parts. First, where is the red x? So you have to first locate the red x and then apply beta reduction to this red x. So that's what this reduction strategy is about. Now let's think about this evaluation context. Evaluation context is basically some expression with a hole in it. And this hole is going to be the position where the next red x is found. So evaluation context tells you where to locate the red x. And this reduction strategy tells you where to locate the next red x. And evaluation context tells you immediately where the next red x is found. You just try to find the hole in this evaluation context. In this regard, these two notions are equivalent. And this example shows that call by value reduction strategy gives us this definition of evaluation context. The whole story here is you can now give just a definition, an inductive definition of evaluation context to specify a particular reduction strategy. So in other words, we just look at this definition, evaluation context, then we can tell right away, oh, this evaluation context corresponds to call by value reduction strategy. So that's the beauty of evaluation context. This single line of inductive definition tells you everything about the reduction strategy you have in mind. In this particular example, it's call by value. And the course notes gives another example. So for example, what is the evaluation context corresponding to call by name? It's very simple again, but this is call by name. From call by name reduction strategy, we can obtain evaluation context, a unique definition of evaluation context, which is whole or kappa E, and that's all. If kappa, then E1 else E2. So if you are currently looking at this evaluation context kappa E, so that means that you have an expression, for example, E prime E, and you are currently trying to find the red x somewhere inside expression E prime. And unlike a call by value, so in the case of a call by value, we have this component, but we don't have something like that here, because in the case of a call by name, if you have lambda x a dot e applied to E prime, the whole expression itself is red x. So you don't have something like this here. So these are two examples to illustrate why evaluation context, an inductive definition of evaluation context, corresponds to a unique reduction strategy. This one essentially specifies a call by value, and this one essentially specifies call by name. Now let's put together all these observations and develop an alternative formulation of operation semantics. So first, as a running example, let's use this evaluation context for call by value. Evaluation context kappa is whole kappa E lambda x a dot E kappa, or if kappa, then E1 else E2. So this definition of evaluation context corresponds to call by value. Now, let's put together all these things and develop the alternative formulation. First, we need an operation that actually fills this hole with an expression. So we use this notation, kappa hole expression E. So the intuition here is you have a kappa, so you have some expression with a hole in it. And now I'm going to fill this hole with a concrete expression E. So that's the idea. So this is of course defined inductively. So for example, hole bracket E is of course expression E because literally find the hole and fill the hole with expression E. So you obtain this one. And what about kappa E? Uh-oh. Uh, let's say this is E prime. And of course this is inductive, E prime. And lambda x A dot E applied to value kappa applied to hole E. And of course this is also inductive applied to kappa E. And similarly, if kappa then E1 else E2. This is another evaluation context with the hole E. Then you literally propagate this one to this position. So it's going to be if kappa E, then E1 else E2. Now we have this new notation, new form of expression. So basically this one is we are decomposing given expression into two components, this evaluation context kappa and expression E. Now suppose that an expression is reducible. We know that this expression E is reduced to another expression E prime. So let's suppose that there is some expression that is reducible. Then what happens is we know that this is reducible. Then there must be unique radix. And this in turn implies that there must be unique evaluation context. And this one is unique because this evaluation context is obtained by removing this unique radix from the original expression. So if this is unique, and the evaluation context is also unique, therefore, this expression should be rewritten as kappa expression EE with hole. This must be unique, and this must be also unique. And this is unique, and also it is radix, so expression E should be reducible by this beta reduction, E prime. And then what happens? We just reduce this radix into E prime, so the result is going to be kappa, where expression E is replaced with E prime. So this is the rule, reduction beta rule. And in this reduction rule, we didn't care about the specific form of kappa. It is a general reduction rule that can be applied to any form of evaluation context kappa. So in other words, we need only this single reduction rule in this new formulation. And finally, we have to do something about this beta reduction. And in the case of our running example, we have three kinds of beta reductions. First is lambda x A dot E applied to value V. This beta reduced to V for X expression E. And if true, then E1 else E2. This beta reduced to E1. And similarly, if false, then E1 else E2. This reduced to E2. So the new formulation of operation semantics is comprised of three sections. First, we have to give an inductive definition of evaluation context. Remember that this single inductive definition of evaluation context specifies a unique reduction strategy. In other words, the reduction strategy is built into the definition of this evaluation context. We can just look at this definition and then deduce, oh, it corresponds to call by value. Next, we need this single reduction rule that covers all the cases of evaluation context. So this is the second component. And finally, we need to list all the beta reductions. So this is the new formulation of operation semantics that consists of evaluation context, single reduction rule, and the list of beta reductions.